All right, welcome back. Let's go ahead and continue with section 3.3.1, uniform random variables. All right, so let's just go ahead and recall that we are examining continuous random variables. And so what I want to do now is I want to attempt to describe as best as I can how this random variable x will behave. So you can go ahead and consider, for example, x is the weight of, let's go ahead and say, a plate of food that comes to the table. Or X could be, for example, the amount of water that is in a cup. Some variables we can go ahead and say are uniform in that the values that we observe are more or less between two given values. So if we go ahead and think of a cup, and let's say we're looking at a cup that fits 16 ounces, then if it's meant to be filled at 16 ounces, chances are pretty good that the most of the measurements are going to be right around 16. So for example, if I make a number line here, so here's my number line, pretend that you don't see the blue, and this is 15.8 ounces, and then over here would be 16 point, let's say 0.2 ounces, or let's just make it easy, 16.1. Then I do not expect to observe a cup that is filled beyond 16 ounces, right? That'll be pretty difficult because it won't fit in the cup, or for it to be filled below, because then it'll be very obvious that it's underfilled. So we can go ahead and say, hey, it could be that the number of ounces in the cup is gonna be between 15.8 and 16.1, but it'll be equally likely to be on the left, in the middle, closer to the right. And so if you go ahead and actually collect a sample, we would expect our histograms to look something like this. Remember that no one spot between 15.8 and 16.1 is favored over the other. And that is what we mean by uniform. So I'm not saying that that's actually what happens in real life. That was just an example. Okay, so let's go ahead and actually look at an example. If there is evidence to say that the value x tends to not favor any spot, but occur equally over some interval, like between 15.8 and 16.1, then we write that x has a distribution that is uniform with parameters a and b, where a and b are basically, you're telling me the value to the left and the value to the right of that interval that we described. So for this example that I gave you, we can write it like this. I can go ahead and say that the number of ounces in this cup are uniformly distributed by writing the tilde, U for uniform, and then basically saying that it's between 15.8 and 16.1. So this writing in orange completely describes this random variable. Remember that there is a big benefit to having named random variables. It means that we know everything there is to know about them. So it's really easy to work with them. More precisely, you can show that the expected value, which remember is more or less the center, is a plus b over 2. In other words, the average of these. So if a is 15.8 and b is 16.1, then the average is literally right between these. So there's mu. And then again, the spread that we observe in our distribution is given by the standard deviation of this random variable. So sigma sub x is given by the square root of the difference b minus a squared divided by 12. And these are formulas that are derived using calculus. So we're not going to be able to show it. You just more or less take my word for it. All right. And what I want to do is I want to give you an example. So let's go ahead and start. Here's an example. Suppose that you're interested in the wait time for a bus. So imagine yourself at a bus stop and you're waiting. Now, here I actually do have some data to give you. We went ahead and collected data from 100 different individuals throughout a given week for the same bus route, same stop around the same time. The histogram for the wait times is given to the right with some evidence that the wait times are uniform. So this is really, really important because I know it's very confusing when students say, well, how do you know that random variable X is uniform? Again, there needs to be evidence of that. And so here I have a histogram. You can observe the x-axis are the times that we observe. They span from 0 to 30 minutes. And we can see that over time, this is relative frequency. So this is how many individuals waited between 0 and 2.5. Then here we observe the relative frequency for individuals 2.5 to 5 minutes, and so on. Notice that there seems to be a distribution that's kind of all over the place between 0 and 30. So the times are dispersed through that interval from 0 to 30. There doesn't really appear to be one time that is very common, and there doesn't appear to be any time that's very unlikely. So here's the wait time. You should have this data under the shared data set, so we can go ahead and use that, unit 3.3. And so here's the wait time. Let me just go ahead and quickly do a dot plot of the wait time. And here's what I mean by that there doesn't really seem to be any cluster of wait times. And there doesn't really seem to be any huge gaps or decay in the frequency of these times. This provides evidence that, hey, maybe the wait time doesn't really have a preference between 0 and 30. And that's what I meant when I said, let's assume that the random variable is equally likely over an interval. Okay, there needs to be evidence for that. All right, now notice that this says, note that people will wait between 0 and 30 minutes for this specific bus. There was nobody that was observed waiting much longer than that. Obviously, this is just for a random sample. We don't really expect this to be true for example, peak times. But for now, we're just going to go ahead and say, okay, let's answer these questions. Define the random variable of interest. So what were we interested in? After some thought, we realized that, hey, what I was interested in was the wait time for this bus. Another way to say wait time could be time to arrival. So X here could be equal to the time to arrival for the next bus. All right. And then I say write this distribution in proper notation. So in other words, what we observed in our histogram and in our dot plot essentially supports the idea that this random variable, that the wait time, is distributed uniformly between 0 and 30 minutes. So this right here completely describes it. Then it says find the PDF and sketch it. So the PDF, if you remember, was essentially the distribution. How can I describe not the sample, but the distribution, the theoretical distribution? So this this histogram that we observe supposedly follows some kind of pattern, and we're here asking, what is that pattern? So for the PDF, there is a formula. It's that the function is given by 1 over b minus a for any given value of x that's between a and b. Don't worry too much if you're struggling with this notation. We're not going to really focus on this. And it's going to be 0 otherwise. All we have to do here is use the fact that when I use this notation, the value on the left is a, and the value on the right is b. So go ahead and substitute, and you'll end up with f of x is 1 over b is 30, a is 0, for 0 less than or equal to x less than or equal to 30, and 0 otherwise. 1 over 30 minus 0 is just 1 over 30. And 1 over 30, we got to find what that is. So I'm going to go to my calculator. Let me pull that up. That's 0.0333. So if I were to sketch this this function, this basically says that you have a function with a height of 0.03. And your distribution will always look like the following. It'll have a height of 1 over b minus a between a and b, and it'll have a height of 0 everywhere else. So it's this step function. I can go ahead and more or less add that onto my histogram here. So we can see that my height between 0 and 30 has to be 1 over 0.3333. So 0.03 is somewhere around here. Notice that they don't match because here we have data. So this is 0.03, and it only occurs between 0 and 30. Let me emphasize this a bit more. And it's going to be 0 everywhere else. So this here is a rough sketch of my distribution. All right, that's about it. Let's go ahead and move on to the next one. So this is where we really want to go ahead and pay attention because we're going to be finding probabilities. And there are ways to do this by hand. I don't want you to do this by hand. There really is no point because we'll be using technology. So for D, I want you to sketch the region of interest given that giving the probability of waiting less than 6 minutes. So remember, the wait time is X. So here they're basically saying, can you sketch something that'll tell you the probability that the wait time is less than 6? So you go ahead and quickly sketch your distribution. Here's my axis. Remember that it goes from 0 to 30, and it's basically a step. So you just go horizontally, then you drop down. So 6 would be, so let's see, half of that is 15. Then half of 15 is around 17.15. So 6 is around here. So if you wait less than 6, you want to shade the region to the left of 6. You're essentially saying I would be happy to get any data that lands here. So we're shading this in. And the reason why this should make sense is remember that we can count, we can find these probabilities by adding, for example, we can do percents. And so I can go ahead and change this to 36. So let's see, a 6 here. Yeah, 6 is somewhere around here. And so we can observe the count that this is roughly 29% of the data lands to the left. That is a probability because we go ahead and take our count divided by the total sample. So that's 29. I'm guessing this out of 100 times. So you can see that 29 out of 100 is this region. And we have this graph here as a histogram. So let's make a histogram. Let's do relative frequency and add our dividers. And note that we have more or less the same concept. Once I get to 6, I essentially highlight all of the values to the left, and this here is the relative frequency, which remember was 29. So slide this down. It's right around 29%. To show that idea, I don't want to use my sample. I will use the distribution, this curve that I did. So that's part of the reason why we're shading this region here. So this in red equals the probability that my random variable x, which is the wait time, will be less than 6. All right, let's go ahead and continue by finding the theoretical mean. That's mu. And remember that there was a formula, so you can just go ahead and look it up. The expected value was a plus b over 2. So write that down. And then we're just going to substitute. Remember that a is 0, b is 30. So if I divide that by 2, that's 15. So that means that on average, I expect that the sample mean will be 15. So that more or less just tells you that your center of this curve is 15, which I'm not surprised because we've more or less been seeing that. Here's 15. Here's 15 here. And you can see that it's more or less in the center. All right, to quantify the standard deviation here, we're going to go ahead and do B minus A. Oh, again, this is the formula. I'm going to go ahead and write this down. So square root of B minus A squared over 12. We're essentially plugging in. This is a calculator problem, so feel free to go to desmos.com/scientific and use that calculator there. So this will be 30 squared over 12 square root. So that ends up being, so just throw that into a calculator. You don't have to do this by hand. That's square root of 12. That's 4 rad 3. So that's 2 rad 3. Anyway, whatever that is, I'm not very concerned about this. Just know that you plug it in and you get a decimal from your calculator. All right, finally. Let's take a look at part F, which is find the 90th percentile. And this is just a quick recap of what percentile meant. So here is my distribution. It goes from 0 to 30. And there's some height. I'm not really concerned with the height. All right, and let me just remind you of what the percentile means. So remember that percentile is essentially the location. It's an X value. It's a value at which the stated percentage of data is to the left. The left of this value. So in other words, there's some value here on this number line, and I want to capture 90% of the data. So just think about this, 90% of the data. Remember, if I cut this in half right here, this would be 50% of the data because it's half. And so this number on the number line would be the 50th percentile. If I want 90%, you got to go further out to the right. So I'm going to mark this. Now, notice I don't know what number that is. So I'm going to put an empty box. I'm going to say there's some number on this number line, but I do know that the area to the left should be 90. So here that I'm shading this area, and that area is 90% of the total. Remember that 90% is 90 out of 100, so that's 0.9. So the area here in red is 0.9. The way that I'm going to find this is I'm going to write out the probability statement. What I shaded here in red is the probability that my random variable x is less than this unknown number. So I'm going to put a box. But that probability, remember, was this shaded region is 0.9. With this probability statement, I can now go ahead and find the 90th percentile using StatCrunch. So let's go to StatCrunch. And let's go to Stats, Calculators, and go ahead and select the distribution that we are using. So from here on out, anytime you guys draw a distribution and you have a probability statement, you're always going to go to Stats, Calculators to find a missing piece. So once I go to Calculators, you recognize that uniform is down here. We're working with a uniform distribution. Notice you see a little box show up. And then you have to type in the lower limit, which is the value a minus 0. So I'm going to leave that alone. And the upper limit, for us, this is 30. All right, I'm just going to press compute so that you can see what happens here. We now have a graph. Notice that this 0.03333, that's the height here. And the x-axis goes from 0 to 30, which is exactly what I've been drawing. Now, check out this probability statement at the bottom. I am going to go ahead and make sure that that probability statement in StatCrunch matches this one here. So I'm going to type in probability that x is less than an empty box. So I want to make sure I delete this. And the value to the right of the equal sign, the value to the right of the equal sign is always the area or the probability. It's 0.9. So I'm going to type in 0.9. And notice how the distribution that we see here in the applet is mostly all red. And what that tells you is that it's shaded 90% of the total area. And notice that there is now this value that is populated. So this value here, 27, is our missing value. That's the value that I was after. So that's our answer. So the 90th percentile is 70 because 90% of the data lies to the left of 27. Let's go ahead and verify what I said earlier, that the halfway point, if you guys remember, that was 15. So I want to verify that 15 is the 50th percentile. To verify that, I would write the probability here that x is less than some unknown value, if I didn't know it, and that would be 0.5. So if I type that into StatCrunch, let's make it match, delete, make sure this one's blank because you're finding the percentile. And the area was 50%. So that's 50%, that's 50 out of 100. You can also type it like that, 50 out of 100. So that's 50%. And if you press compute, you can see that we have the value of 15. And it's clear in this example because half of 30 is 15. And remember that this area here is more or less uniform throughout. So all's well. All right, let's go ahead and find the following. Let's find the probability that you wait less than 15 minutes, given that you've already waited less than 10 minutes. This problem, by the way, is just an exercise in chapter 5, the probability section. So it's not something that I really want to emphasize here. Let's go ahead and find the probability that you wait less than 10 minutes first. That x is less than 10. Let's just go ahead and find that first. Go ahead and use StatCrunch to find this. So probability that x is less than 10. Visually, I want to sketch this number line going from 0 to 30. And then I want to find where 10 is at and go ahead and shade this in. And remember that the area is the probability. All right, remember that we go to stats, calculators, uniform. We type in our parameters, which for ours was 0 to 30. And I basically go ahead and make sure that this probability statement matches my paper. So that's the probability that the random variable is less than 10. So I want to make sure I put a 10 right here. Press compute, and we have our answer. All right, so there's my answer. I'm going to ask you to complete a problem. So if you need help, please rewatch this so you can see how to do that for some points. All right, so hopefully you've done that problem. Let's now go ahead and just, for completeness, see how to do this problem. So this problem is a little challenging. It says find the probability of waiting less than. So this is the probability that I wait less than 15 minutes. Now notice this is given, so I'm going to put the vertical bar. I've already waited 10 minutes. So this means that x, the wait time, if I'm already waiting 10 minutes, it now means that this wait time has to be more than 10 minutes. So x is greater than 10. So think about that for a moment. That's what I'm trying to find. Now I'm going to go ahead and use my probability rules. I know conditional probability. So this now is going to be equal to the probability. So we got to remember that the probability of A given B equals the probability of A and B divided by the probability of B. So here I'm basically going to write the probability that x is less than 15, x is greater than 10, divided by the probability that x is greater than 10. So it's just the probability rule for conditional probability. Pay attention to the top. To this right here. This is saying that you're weighting less than 15, but you're weighting more than 10. So this we can actually write as the probability that 10 is less than x and that x is less than 15. So that means the same thing. It means that x is somewhere between 10 and 15. And that should make sense if you say it out loud. When we translate the orange text, which is probability x less than 15 and x greater than 10. So that's literally the probability that x is between 10 and 15. And then I'm going to divide this by the probability that x is less than 10. Oh, sorry, greater than 10. All right. Now, this probability that x is between 10 and 15, we can actually use StatCrunch to find that. So if you're only looking at one-sided probability, so probability that x is less than or greater than a number, that's fine. But if you want to find probabilities between these, go ahead and toggle this button here where it says between. So if you click between, it'll now give you two options. So what's the value to the left? For us, it was 10, and the value on the right was 15. I'm going to hit enter. And notice that the graphic matches exactly what I wanted. I want any value that lands between 10 and 15. And that area is 0.1666. All right, and we actually have the end of this because now you can find the probability that x is greater than 10. So the probability that x is greater than 10, going to go to standard, change this to greater than. And now you can see here, this says the probability that x is greater than 10. Look at the graphic. There's a reason that it's there. It's shading everything from 10 to 30, which is good for us because that's the correct region. And the area 0.666. All right, so now we just got to throw that into a calculator and you will get your final answer. So go ahead and throw this into a calculator, 0.1666 divided by 0.666. And go ahead and type in what you get. All right, so this was a complete problem using the uniform distribution. I'll go ahead and run through one more in the next video. If you have questions, please make sure to reach out.